Hello, everyone. Thank you for listening to my honors capstone presentation. My name is Julian Tarazi. I am a senior in aerospace engineering here at the University of Michigan. And for my capstone project, I decided to get involved in the multidisciplinary design program, where I was one of five team members working on the Collins Aerospace Galley thermal and power optimization team. So over the next few minutes, I'd love to present to you the work that we did. So in terms of the big picture of the problem we were trying to solve, um, galleys, which are the kitchen or the food preparation area on an aircraft, actually represent the largest electrical load and are also responsible for releasing substantial waste heat to the cabin. And these inefficiencies end up resulting in excess fuel consumption. An airline Collins deliver a more efficient galley system to its customers, but its customers, those airlines, can then save on fuel costs, reduce their footprint, and moreover, this can help with this general industry shift towards more electric aircraft, which is seeing the replacement of outdated hydraulic and pneumatic systems with more modern electrical ones. Being able to reduce some of the power, in the galleys will help mitigate the anticipated increase in the power demands that is likely to result. Here are two images. One, on the left of an aircraft galley, just the kinds of galleys that we were looking at for this project. And the image on the right is an example of the devices called inserts that Collins Aerospace produces and sells to customers, and is what we were working with for this project. The overall goal of our project was to reduce the power consumption of the aircraft galley system. There were numerous requirements that came off of this, a few critical ones as well, but really the two most important ones that it came down to was that we were looking for a reduction of 10% in average power consumption and a reduction of at least 25% in peak power consumption. Now that begs the question, how did we validate the performance of our solution? We didn't have access to a physical galley, and the limitations posed by COVID-19 just introduced even more restrictions and made it that much more difficult. Well, our solution was to build a power consumption model of the galley for us to use in our analysis and in our solution development. So the first, bit of work that we had to do for the project was to research and collect information on galleys. While Collins is aware that this is a problem, they don't have a lot of data on things like typical insert usage over the course of a flight. So we had to do a lot of research to help understand that, and also understand the thermal and electrical characteristics of each of these inserts. We then built a model that mimics an existing Airbus A350 galley's power consumption over a typical flight, developed solution concepts from the results of that model to help reduce the power consumption, and then integrated those solutions into the model as a means of validating their performance. So in terms of the power consumption model that we developed, it simulates a typical 8-hour flight and uses probability distributions to create unique parameters that govern passenger needs for a specific flight. Essentially, how frequently and for how long are different inserts needing to be used. And this introduces a kind of Monte Carlo approach to the problem we were trying to solve. And it also guarantees uniqueness between simulations. We didn't want to develop solutions that were over-tailored for one specific type of flight. The model also incorporates realistic thermal models of each of the inserts so that we can model their behavior and also simulate the thermal interactions between inserts that are close to one another. The model is designed so that solutions can be integrated into it easily, which not only helped us in developing our solutions, but it's adaptable to any new or modified solutions that may come in the future. And finally, it tracks the associated power consumption of each insert so that we can actually analyze what's happening over a typical flight and see how our solutions are performing. In terms of the solution concepts that we studied, the first was an improved aerogel insulation for the chilled cart bays. This aims to reduce heat loss through the cart bay walls, and in addition, it is lighter than the existing insulation in the galley, which is beneficial for weight reduction. Additionally, we also looked at a variable cart bay airflow solution, which was essentially to only provide cooled air to occupied cart bays. In its current state, the galley system redirects cold air to cart bays, even if those carts are out, up and down the aisles of the aircraft being used. And finally, we looked at the implementation of a power management controller, which sorts incoming power requests from inserts based on the priority of that request, and then distributes power back to only a subset of the inserts in order to avoid violating some sort of maximum threshold. This was aimed at reducing the peak power consumption. And the controller also shuts down inserts that are idle in standby mode for extended periods of time. That's aimed at reducing average power consumption. And this solution opportunity presented itself because the current system doesn't monitor power demands. It just gives or grants power requests, whenever they're made. In terms of validating the performance of our solutions, we created a validation script that runs 100 simulations of both the baseline and solution galley architectures. And for each one of these runs, it uses the same randomized configuration that I was speaking about earlier for both architectures, so that we can ensure that we are making like comparisons between runs of the original galley and the one that includes our solutions. In terms of the results of the project, as I mentioned at the beginning, our goal was to reduce average power consumption by 10% and peak power consumption by 25%. We were able to achieve both of these goals, getting 12.8% on the average power consumption and 27.4% in the peak power consumption. And the two graphs I've included on this slide, on the left just shows the power consumption over the original flight, and on the right what it looked like with the solutions being implemented. And you can see the difference, especially in peak power consumption, where the solution peaks a little above 8,000 watts as opposed to 12,500. In terms of the implications and next steps of our work, the model that we developed is now a tool for Collins Aerospace to employ as they wish. They, can further develop the solution concepts that we've explored and provided for them, but it also provides a framework for them to rapidly test any new concepts that they may come up with. In terms of the longer term implications of this work, the reduction in power consumption ultimately results in fuel savings, and additionally the lower power peaks means that a smaller generator could be used, which reduces weight further and thus creates even more savings. The fuel savings also help with the reduction of emissions and ultimately can enable cheaper air travel. And finally, these solutions create more energy availability for other onboard systems, particularly new ones that may come about as the industry shifts to this concept of more electric aircraft that I touched on at the beginning of the presentation. Just in terms of some acknowledgements, here at the end, I'd like to extend a big thank you to PC Koo, who was our faculty mentor through the MDP program, and also Matt Pearson, who was our sponsor, mentor, and main point of contact at Collins, and without whom this work would just not have been possible. So I'd like to thank both of them a lot for their help throughout this process, and I would like to thank you all for listening to my presentation. If you have any questions, feel free to leave them in the comments below. Thank you.